fastest code in the world. That is a bold claim. But what do I mean by fast? How fast is fast? Well, I come from the world of networking. And in networking these days, 100 gig NICs are really common. But what does 100 gig NIC actually mean? Well, if you make some assumptions about packet sizes, 100 gig NIC is about 10 million packets per second. 10 million packets per second, if you do a bit more maths, you get to 100 nanoseconds. So 100 nanoseconds is your time budget for processing a packet. Let's put that in perspective. A beam of light going from the stage, by the time it gets to the windows at the back of the room, you have to finish processing a packet. We're at a tech conference, so let's put it in clocks as well. We've got 300 clocks of our CPU per core in order to do this processing. So that's what I mean by fast. So what are we going to talk about today? We're going to be looking at 7 different techniques, and we're going to be taking a practical look. So I've actually gone and written some code for this presentation, and we're going to be working through that code. We're going to be looking at those optimizations, going to making the changes to the code, and seeing what effect it has. All right, let's step back a bit and do some introductions. So I'm Alan. How did I get here today? Well, with difficulty because of the train strikes yesterday, but actually how I got here today, I've spent about 15 years working in the networking industry. I'm currently working for Microsoft for Azure for Operators, where our mission is bringing the power of the cloud to network operators. So let's make that real with a little bit of an example. So who here today has been using their phone and has actually got 5G connectivity? Yeah, loads of people. So what actually happens, data from your phone when you've got 5G? Leaves your mobile phone, goes to the radio network, so a mobile tower somewhere around here. And then from that radio network, from lots of different access points in that radio network, it all gets aggregated in this thing called the 5G packet core. Now, the 5G packet core, that is really the brains of the operation. That's where all the smart stuff happens. At least, that's what someone who works in the 5G packet core will tell you. So let's zoom in on the 5G packet core. What's actually happening here? So data comes in from the radio network, and it's encapsulated. So the packet your phone's trying to get to the internet is that dark blue packet at the bottom, an IP packet. But it's encapsulated in all these extra headers. And what are they actually doing? They're telling the packet core who this packet is from. So is this packet from Bob's phone? Is it from Alice's phone? What's the session, and how should that packet be treated? All that information is in this GTP header. So what the 5G packet core does is it's going to match on all that information in the header, and then it's going to apply policy. So all that policy might be things like applying quality of service, or it might be doing NAT, network address translation. It could even be doing something like lawful intercept. And finally, what it's going to do, once it's decided how it's going to treat that packet, it's going to rewrite the headers and then send that packet out to the internet. And that's how you're browsing the BBC News or whatever it is from your phone. Now, I'd love to do an example today with a real 5G packet core, but it's far too complicated. So what we're going to do today is we're going to use a really simplified version, and we're going to look at the code, and we're going to keep iterating that code, adding in performance optimization techniques, and measuring what difference they make. So here's my simplified example. I'm calling it a packet processing device because I'm not in marketing. So what we're going to do is we're going to match on the header. We're going to, based on that match, apply a rewrite policy. We're going to rewrite parts of the header. So you can see I've colored in some parts of the header here and not other parts. So what we're doing there is some bits of the original header we want to keep, some bits we want to rewrite. So let's start simple and actually look at some code. Now I've written all of this code in C. Hopefully it's pretty self-explanatory that whatever language you work in, you can understand this. And I've actually even written some comments, so it's probably better than most code you're used to looking at. Yep, definitely some software engineers in the room. OK, this is the main function. This is the function that's going to get called every time our device receives a packet. It's actually really simple. We're going to get a lookup key from the packet. So all that data in the header, we're going to build a lookup key from it. Next, we're going to perform the lookup. Now, I'm starting off really simple here, so I'm just using a standard unordered map from the C standard library. It's going to be really simple. Based on the result of the lookup, we get a match structure. That match structure tells us how we need to rewrite the packet. Then we're going to call our apply rewrite function and actually rewrite the packet. And that's all there is to it. It's really simple. So how does this perform? So I measured this in a micro benchmark that I wrote. It's about 1,000 clocks per packet. So we're spending 1,000 clocks to process every single packet. Now, if you remember back to the beginning, I said fast has got to be at least 300 clocks per packet. So I'm going to call this slow. And that's probably not unsurprising because we haven't done any work on it yet. So let's now start trying to optimize that code, bringing in different techniques. And I know this is the first talk of the day, apart from the keynote, obviously. So we're going to start really simple. We're going to start with a nice, easy one, something called an inline function. So if we look at this process packet function, this is a function that is going to be called an awful lot. We said about 10 million packets a second. So every second, we're going to be calling this function 10 million times. But what does calling that function actually look like? Well, there's the actual interesting work that we want that function to do. That's the green box in the middle. But there's a bunch of overhead that comes from that function call as well. So for example, we're going to have to push the arguments of the function onto the stack or into registers. We're going to have to put the return address onto the stack. We're going to have to jump to the code that we want to execute. And then we've got to clean up as well. We've got to undo that function call. We've got to pop the address back off the stack. We've got to jump back to where we want to execute. We've got to clean up those arguments we pushed onto the stack. And all of those blue boxes, they all cost you performance. So if you inline a function, you can get rid of all those overheads, and you just do the interesting work that you care about. And the good news is it's really easy in your code. So varies by language, but in C, there's the inline keyword. And then, for some reason that I've never figured out, that's actually just a recommendation to the compiler. So if you actually want your code to inline this function all the time, you need to use the always inline attribute. So here we go. We add a little bit to our function definition, and we can improve the performance. It's not much. We haven't made a massive gain here, but we're just getting started. Bear with me. OK. At this point, as I was writing this code, I was a little surprised that I wasn't getting better performance than this. And that's when I remembered that I really should have turned on compiler optimizations, because the compiler is good at optimizing code. We should let it do the work. I would be astonished if everyone in this room didn't compile their code with O3, at least their production code. Does anyone not use O3? No, OK. But what about the target architecture? How many people set the target architecture for their code? Anyone? Anyone not do that? Yeah, OK, so there's a few hands coming up. So what does this do? So in this case, I was running my benchmark on my laptop there. It's got a Skylake chip in it. So I set the target architecture to Skylake. And that allows the compiler to use some additional instructions. And the key ones I want to pull out from this list are the ones that start with AVX. So the AVX instructions are the vector instructions. So what I'm doing by specifying the target architecture is I'm letting the compiler use those AVX instructions. And we're going to look at those in a bit more detail later, but they are really good for performance. OK, I've got one more here. The M branches within 32-byte boundaries. How many people use flags like this compiling their code? Some people? All right, so this is quite a specific one. There was a bug in Intel chips called jump conditional code erratum. And Intel fixed that with a mitigation. But that mitigation causes the decoded iCache to be flushed if your branches are not aligned on 32-byte boundaries. If your decoded iCache gets flushed, that means you're going to get more iCache misses, and the performance of your code is going to go down. So in our case, on certain target architectures, this compiler flag gives us about a 7% performance boost. I think the general point here, though, is there's all kinds of special compiler flags like this. If you really care about performance, have a look at what there is and know what your system is so you know what might be useful. All right. Hey, turns out the compiler is really good at optimizing code. Awesome. So we're down to about 400 clocks per packet now. We've made a really significant difference there. But we're still not at our 300 clocks per packet. We can still go faster. And those of you who are observant will notice I've got lots more space on this graph to fill in. So we're going to keep going. So I mentioned those vector instructions as part of enabling the compiler to use them. But we can also use vector instructions by hand. So what is a vector instruction? Well, a vector instruction is an example of single instruction, multiple data. It's something that GPUs use, which is why they're so good at training AI models. So let's have a look at a quick example. Here's a vector instruction called VP AND. So this is a vector instruction that does a logical AND on multiple bits of data at the same time. In this case, it operates on vectors. And these vectors, in the case of AVX2, are 256 bits long. So we can pack 8 integers into each of those vectors, and we can do a logical AND for 8 different integers all at the same time with one instruction to get an answer. And again, we get the answer in a vector. So how can we use these vector instructions in our code? So let's go back to our code. This is the main function again, processing a packet. So this apply rewrite function, I didn't expand the details of this before, but let's have a look at what that actually looks like. You can see I've used the inline optimization there already. But what we're doing here is we're going to loop over all the 32 bytes in the header. For each of those bytes, we're going to AND the data with a mask. So that's going to keep the bits in the header that we want to keep and zero out the ones that we don't want to keep. And then we're going to OR in the bits we want to rewrite. So the bits we want to overwrite on top, we're then going to put those in. And hopefully you can see here that this looks like something we could vectorize. We're looping over lots of different bits of data, and we're performing the same instruction each time. So how can we use vector instructions to do this? And the answer is we use something called Intel intrinsics. So Intel intrinsics are just some functions that Intel provide, which makes it easier to use these low-level vector instructions. So what does the code look like now? Now, to be totally honest with you, the first time I saw these in code, it absolutely blew my mind. So I'm going to talk you through this nice and slowly. So the first thing we're going to do is we're going to load the data from the packet, and we're going to put it into a vector. So vector instructions operate on vectors. We need to get the memory into a vector. Then we're going to use an AND, the VP AND instruction, to AND the data from the packet with the mask. So we're going to zero the bits we want to rewrite and keep the bits we want to keep. Then we're going to do an OR. So this is where we OR in the rewrite value for the bits we want to rewrite. And finally, the data we've got is in our vector still, so we need to put it back into the memory where the packet is. So we have to store it. Now that was pretty good. That was using AVX2 instructions. We can actually do even slightly better using AVX512. So AVX512 is the next iteration of vector instructions. And they introduce something called ternary logic operations. And a ternary logic operation lets you do binary logic between 3 arguments at the same time. So in this case, the magic hex 96, good luck working that one out, means A and B or C. And so that will probably save us 1 clock per packet over the AVX2 version. So it's slightly better. We'll go with that one. So how does that do for performance? I was hoping for a lot better than that. We did quite a lot of work there, right? So what's gone wrong? Well, what's gone wrong is the compiler is a lot smarter than us, it turns out. And the compiler is already using those vector instructions. So here's the code from our rewrite packet function. And this is the code from before we vectorized it. And in the box here, you can see the assembly that's been produced. And you can see the bold here. You can see the compiler has already decided it's going to implement this using a VP AND and a VP OR. And so yeah, the compiler's already done the work for us, so we get hardly any performance improvement from these vector instructions. It's not always going to be the case, but in this example, we haven't actually got any benefit from it. OK, we're going to have to start working a bit harder now. Let's look at our data structures. So at the beginning, I said we were just using a standard hash map. And there's been loads of research done on different data structures to enable fast lookups. And what we're going to look at today is a data structure called a Swiss table that Google came up with. Now, I'm going to give a really brief introduction here, but there are some really good videos out there on the internet. So if you're interested in this, do go look them up, because there's some great presentations on it. So how does a Swiss table work? It's a hash table, so we've got a hash. But what we do with that hash is we split it into two different bits. So we've got an H1 value, which is the first part of the hash, and we've got an H2 value, which is the second part of the hash. What the H1 value does is it identifies a group. And that group does two things. First of all, it tells us which bucket our entry is going to be in, the actual thing we want to find. And the second thing it does is it points us to a metadata array. Now, this metadata array is one of the key things here. That contains the packed values of all the H2 hash values of the entries that we've put in to the bucket. And so what we do then with our H2 hash value is we look in the metadata array, find which one matches, and then that lets us jump straight to our correct entry. And whenever you're talking about a lookup and someone says jump straight to, that is a good thing. So let's have a little look at what's going on, just kind of simplified, because I've gone very quickly through that. What we're doing here is, number one, we calculate a hash. Number two, we get the metadata array based on the value of H1. Number three, we go through that metadata array, comparing the H2 hash value with the different metadata values. And then depending on which one matches, we jump straight to the entry. So why is this good? Why is this going to be more performant than our standard hash map? Well, first of all, it's really cache efficient. So in this implementation, we've only got two memory indirections. We've got one memory indirection to find the metadata array, and then we've got one memory indirection to actually get the entry. And that's going to be significantly better than a standard hash map. Now, the second thing that's good about this is we're doing our probing of entries using these H2 hash values. So in the mainline case, we don't have to compare key values, apart from for the final entry that we find. And the other good thing about this is that packed metadata array, if I just jump back a couple of slides, there's 16 entries in there. We're doing the same operation with lots of different bits of data. And so we've already talked about vector instructions. You can do that comparison really, really efficiently by using vector instructions. And so you spend very little time probing your entries. So let's look at the code. What does it look like? It actually looks really similar to the standard hash map. We're going to extract the lookup key. I've got a slightly different format lookup key just because of the Swiss table implementation I used. We're then going to perform the lookup. I'm not cheating here. I'm using exactly the same hash function, which is a significant part of the cost. So I've used the same hash function, so it's all fair. And then we're going to apply the rewrite, exactly the same as before. Does this lookup do any better, though? And the answer is yes, it does. It does significantly better. So we're dropping from about 400 clocks per packet to about 300 clocks per packet. So we're getting a really good performance boost from using this new data structure. OK, moving on to the next one. We're starting to have to work really hard now. So this is the point of the presentation where everyone has to start paying attention, because it's going to get more difficult. Good. It's still early in the morning. Everyone's ready. So interleave processing is the next thing. So I talked a little bit on the Swiss table about how cache efficiency was really important. And with this interleaving technique, we're going to look at that in more detail. So when your program's getting memory, you can't get that memory immediately. There's a memory latency. And the memory latency that you have depends on where you're getting that memory from. So if you get the memory from L1 cache, it's really fast. but L1 cache is tiny. You can't put very much stuff in there. If you get your memory from main RAM, it's really slow. The 200 clocks there, approximately, is going to blow our budget of 300 clocks. But RAM's massive. You can keep loads of data in there. What we're going to do with interleaving is look at how we can minimize the effects of this memory access latency. So let's look at an example. So our packet processing, what are we doing as we're going through processing this packet? We're going to process packet 1 for a bit. We're then going to get to the point where we need a bit of memory, which we don't have hot in cache. So we're going to stall for a bit. We call it a memory stall while waiting for the memory. And then we can carry on processing packet 1. And then we start processing the next packet. So now packet 2. And exactly the same thing happens. We get to the point where we need the memory we don't have. We have a memory stall. We wait for a bit. We get the memory. We can continue processing. So now let's look at this with interleaving applied. So with interleaving, we're going to start processing packet 1. We're going to get to the point where we need some memory that we know is not going to be in cache. Now, instead of continuing processing packet 1, we're instead going to issue a prefetch instruction for the memory. Now, what this does is it goes and gets that memory and puts it into L1 cache. And instead of carrying on processing packet 1, we're going to start on packet 2. So packet 2 is independent. We can start processing that. And similarly to packet 1, once we get to the end of that first bit processing, when we get to the point we need some more memory, we're going to prefetch that memory, and then we're going to go stop and do something else. Now, by this point, the memory that we need for packet 1 is going to have made it into L1 cache and is going to be nice and hot. So we can just finish packet 1 processing now. We don't have to wait. We don't have that memory stall anymore. And then we can do exactly the same for packet 2. Because while we were finishing processing packet 1, we've given time for the memory to get into L1 cache. And what that means is we end up saving significant amounts of time because we're not suffering these memory stalls. Now, it's worth saying I've significantly simplified this picture. So the execution unit is going to be doing a bunch of stuff to try and stop your program suffering memory stalls like this. So it's going to be using parallel instructions. It's going to be using out-of-order execution. It's going to be using pipelining. And all those techniques, that's very similar to what we're doing with interleaving. The thing is, with interleaving, we, the program writer, know exactly what our code's doing. We know the intent of it. And therefore, we can do an even better job than the execution unit can do. So let's have a look at what that looks like in the code. So this is the bit where everyone has to start paying attention. So our main function is now no longer process packet. We're now going to process a burst of packets. So for this example, I've used a burst size of 20. So we're going to take 20 packets at a time and process 20 packets in a chunk. We're going to loop over all the packets in that burst. We're going to loop over those 20 packets. And we're going to start doing the processing in exactly the same way as we had for our previous bit of code. We're going to, number 1, extract the lookup key. And then number 2, calculate the hash for the packet that we're going to need. But this is then where it changes. Instead of actually going and doing the lookup, this is the point where we know that memory that we need for the lookup is not going to be hot in cache. And so instead of actually doing the lookup, we're just going to prefetch it. So this is actually prefetching that metadata array for the Swiss table. So we'll prefetch that metadata array, and then we'll carry on. And we'll go through and process the other 19 packets in our burst. And then we get to the next bit of code. So the next bit of code, we're going to start looping again. And at this point, we're going to actually do the lookup. So this is where we actually do our lookup. Now, if we think about packet number 1 in the burst, packet number 1 we calculated the hash value, we built the lookup key, calculated the hash value. We've then issued the instruction to get the memory we need for the lookup. And in the meantime, we've gone and extracted the lookup key and calculated the hash value for the other 19 packets in that burst. So by this point, our memory is going to be nice and hot in L1 cache, and this lookup can be nice and fast. And if only it stopped there, because the same idea keeps going throughout the code. So now you can see I'm not just going to move on to doing the rewrite next, what I'm going to do is I'm going to prefetch the next bit of data that I need. So in this case, it's the match structure, the thing that's going to tell me how I'm going to rewrite. I'll prefetch that. And I'm not going to keep showing the rest of the code. But the rest of the code keeps going in this pattern where we just do a little bit of work on each packet and then prefetch the memory need and then move on. And you can see this has an enormous impact on performance. So we've gone from about 300 clocks per packet, which we thought was pretty good. We're now at 80 clocks per packet. And the key takeaway from this is that memory and accessing memory is expensive. So if you want to speed up your code, techniques like a Swiss table, which are cache efficient, and techniques that stop you having memory stores are really powerful techniques for improving your performance. All right, so we could rest on our laurels here and stop. We've still got one more space to fill on our graph, so let's keep going. We're going to use a technique called loop unrolling next. So let's have a quick look at what our code looks like now. So after we did our interleaving, our code looks a lot like this. We have lots of these loops where we evaluate an end-of-loop condition and then increment or decrement an index. And all of that costs, right? We're not getting that for free. We've got to do some work to do that. Loop unrolling looks at reducing the cost of these loop overheads. So instead of doing one big loop where every time round we're processing the next packet, we're going to do a smaller loop where each time round we're going to do 2 packets or 3 packets or 4 packets. So what this does, in this case, I've loop unrolled to a factor of 2. So each time round we're going to process 2 packets. So in the best case here, where we have an even number of packets, I'm going to have halved the costs of evaluating my end-of-loop condition and incrementing or decrementing my index. The other good thing about loop unrolling is I've now got this bit of code in the middle where I'm doing an operation on packet 1 and then doing an operation on packet 2. And those operations are often going to be independent. Because I've now got them next to each other, the execution unit's going to be able to use parallel instructions to hopefully improve the performance of this even further. So let's have a look at what our code looks like. And I mean, quite frankly, it's horrible, isn't it? If you sent this to me for review, I'd probably send it back to you. Let's have a look at it and see what it actually is doing. So you can see here I've loop unrolled to a factor of 4. So I'm doing 4 packets each time through the loop. But actually, the code is very similar to what we had before. We're extracting the lookup key. All we're doing is we're extracting the lookup key 4 different times for 4 different packets. We're then calculating the hash. But again, we're calculating the hash 4 times for 4 different packets. And then finally, we're doing our prefetching of that Swiss table memory that we need for 4 times through. I'm not going to show more of the code because it carries on in this vein. The other thing to note, though, is we can't guarantee a burst has a multiple of 4 packets in. And so we also have to write even more code, which is really a repeat of the previous code, to handle if there was an odd number of packets in the burst. But it does have a good effect on performance. So we're now down to 65 clocks per packet. And this looks really small on this graph. It looks like a really small difference. But this is going from 80 clocks to 65. And when you're only down to 80 clocks, gaining 15 is a really significant boost in performance. So this is actually a big win here. All right, let's pause there, take a minute to look at what we've achieved. 16 times faster. So from our starting point of 1,000 clocks per packet, we're now 16 times faster at just 65 clocks per packet. And that's all from applying these 6 different techniques. Now I can see people getting up at the back. Hopefully, they've all rushed off to go and implement this in their code immediately, rather than just getting a bit bored. But wait, come back. Before you go, there's a caveat. If you implement all these techniques, it might not always give you a performance boost. And that's because there are trade-offs. And I've kept things simple through this talk up until now, and I haven't talked about the trade-offs. So let's look at a few examples of that now, because these are things you need to be aware of if you're going to do this to your code. The first one is instruction cache misses. So if you use techniques like inlining or loop unrolling, they make your code bigger. Inlining, we're putting that copy of the function in every place it's called from. Loop unrolling, well, you've seen how much more code we wrote for that. That increases the size of your program. That makes you more likely to get instruction cache misses. If you get instruction cache misses, it can slow your code down. As an example, in my team, we've actually removed most of the loop unrolling we used to have in our code because we found it actually improved performance to get rid of most of it because we think of the instruction cache. Another one, cache eviction. So if you prefetch too much memory, that L1 cache is only really small. If you're not careful, you can prefetch some memory, and then before you actually get around to using it, you've prefetched a load more memory, which has kicked it out. And it's not in cache anymore, but you did work to get there. That's not going to be good for performance either. So again, we've actually removed some of our prefetching and maybe just prefetched into L3 cache in order to trade off these benefits. AVX throttling, another one. So when you use AVX 512 instructions, they can be really fast. We've seen how they can improve performance. But if you use AVX 512 instructions heavily, it actually slows down your CPU clock speed. And slowing down your CPU clock speed is not good for performance. And finally, code maintainability. So I just illustrate this with a quick snapshot. Please don't try and read any of this. Of what the codes look like. On the simple code, that's what we started with. Our main function had like 3 function calls in it. It was more comment than code. Interleaved blew that up significantly. Unrolling blew that up enormously. That unrolled code, it might be better in some languages, but in C, it's absolutely horrible to maintain. So those of you who were paying attention might have noticed I said 7 techniques at the beginning, and I only talked about 6 in the previous slide. So that brings me to the last technique, which is actually what we've been doing all the way through, which is benchmarking. If you care about performance, benchmarking is really, really important. You have to be measuring your performance, iterating on it, and then measuring it again in order to keep making those improvements. Okay, so everyone's here to learn something. So what can you learn from this session? Should you go and rewrite all of your code? I hope everyone here has picked up some techniques that you might find useful. But what I actually want to finish with is getting you to ask the question of whether you should use these techniques or whether you shouldn't. And so this is my attempt at a single slide to summarize what can you learn from the fastest code in the world. So what do we have here? We've got a graph where on the left here, we've got techniques that are really simple to implement. They don't take much time. They're relatively simple. On the right, it goes to complex techniques, things which are hard to implement, things which take time. They're bad for maintainability. On the y-axis, we're going from low-impact techniques at the bottom to high-impact techniques at the top, things that have a really big impact on your performance. So let's look at the different quadrants. So this quadrant in the top left corner, these are things which are pretty easy to implement and have a really high impact on performance. You should all just go and use these. It's a no-brainer. Might be a few people going, data structures. Was that easy? That looked like he wrote a load of code in the background to implement the Swiss table. And you're right, I did write a load of code in the background to implement the Swiss table. But actually, in most languages now, you can use these data structures for free. So I mentioned Google came up with this. So if you write in C or C++, you can use the Abseil project, which Google have open sourced. you can use a flat hash map, which is a Swiss table. For those of you who write in Rust, I found out the other day that the Rust default hash map implementation actually uses a Swiss table under the covers already. So you may even be using some of these data structures without knowing it already. Techniques that fall in these diagonal quadrants, so things which are easy, low impact but really simple to implement, or high impact but quite hard, these are the ones you need to think about. These are the ones where it might be worth doing this, but it might not. And here you have to think about efficiency in the broader sense. How much is it going to cost me to develop this? How much is it going to cost me to maintain this? How much is my code going to be deployed? Is its runtime performance benefit going to be worth the extra effort I put into developing it? And so probably you're not going to use these unless you have an application that performance really matters or where it's really widely deployed. Or maybe this is something where if you're writing a greenfield project from scratch, you would try and use some of these, but you're not going to go and rewrite all your existing code to try and add these in. And finally, there's the stuff that is both relatively low impact and complex. Quite frankly, you just shouldn't ever bother with doing these. All right, so that is my final slide for summarizing what can you learn from the fastest code in the world. Please do vote and leave feedback. We've now got some time for questions. So if anyone's got a question, please stick your hand up and we'll get mics to you.
Yes. Hi. What is your view on frameworks that will automate the generation of this super optimized code?
Sorry, I didn't see that question. Where's it?
Sorry, here. No, what is your view on frameworks that will automatically generate all this highly optimized code?
So the question was, what's my view on frameworks that will generate this highly optimized code?
Automatically based on benchmarks that will run automatically for you on.
So I haven't found any frameworks that will automatically generate this code that performs at this level that we've got to here. If you know of frameworks that can do that, I'd love to hear about them.
Yeah, there are a few in academia, but indeed not in the...
Okay.
Hey, I wanted to ask about the prefetch stuff. Like, how do you know that the prefetch is finished? Are you like going through and actually counting instructions? Isn't it kind of fragile? And I guess similar question for the cache thrashing problem. Like, you have to tune some parameters to know whether you're thrashing the cache or not. Doesn't it all get kind of fragile when like compilers change? Like, how does that actually work?
Yes, just repeating it so it's on the recording. So there's a couple of questions there. One is about how do you know prefetching, like how do you know when you've waited long enough? Do you have to count the cycles? And then also some follow-on questions about thrashing the cache. So certainly in our code, we don't count the cycles. We essentially pipeline all of our code so that we're pretty sure that by the time we need the memory, it's going to be there. One of the things I didn't go into the talk in detail because we didn't have time, but there are some great tools out there where if you are running performance benchmarks, you can get lots of information about whether you are seeing memory stalls. So we use vTune. I don't know if other people use that as well, but that's a really powerful tool for telling you if you are hitting memory stalls and then allowing you to iterate. The thing I would say is this really illustrates the point of performance benchmarking. So if you don't have regressible performance tests that run as part of your CI suites, then yes, it's very fragile because you can regress performance really easily. So one of the key things that we do is we invest heavily in that CI/CD performance regression. So every time any code goes into main, it's running performance tests, and if they don't pass, the code doesn't go in. Question in the front.
Hi, brilliant talk. Thank you so much. I have one small question. So here, the seventh mentioned technique was benchmarking. However, I believe there's like a law in physics that says if I'm measuring something, then I'm affecting it. So what's your point on that? Like, how is it improving us instead of improving the performance instead of regressing it?
Yeah, good question. So the question was about if we measure something, then we affect it. So if we're doing benchmarking, how do we know we're not affecting performance? The answer is, from my opinion, you have to do lots of different types of benchmarking. So in the example that I've gone through throughout this talk, we've really been doing a kind of micro benchmarking. So I built an infrastructure around the code and counted the clock cycles for looping over it lots of different times. We saw a really good performance improvement from loop unrolling. I think if you put that in a bigger application, you wouldn't see the same performance improvement from loop unrolling because you would start having problems with iCache. And when we're just using our micro benchmark, you don't have any problems with iCache because it's just a small program. So if you measure things in different ways, so you have micro benchmarks where you can iterate quickly and very quickly turn around performance changes and try things out, but then also have on the other end of the scale performance tests where you're testing really the whole solution and seeing does it work end to end, then the combination of those can help mitigate some of those problems. Okay, any more questions?
Hello. In high-level programming languages, normally I mostly use C#. You don't have this level of control of the optimization. So which could be a good strategy if I have something that need to be very performant?
So the question is, if you're using higher level languages and you don't have this level of control, what can you do about it? So I think it probably depends on which higher level language you use. So Rust is something I use a little bit, and I think Rust does actually have ways of calling Intel intrinsics directly from Rust, for example. I'm not familiar with C#. I think probably when you start a project, you've got to make a decision about what language you use, and if you're really looking for something fast and efficient, you choose an appropriate language. Yeah, you're not going to use Java or C#. Yeah. Any more questions?
Okay.
So I have a question. You've put the benchmarking part on the 7th step. As you told, in the end, you need to do benchmarking at every steps. I think a warning can be added about premature optimization, because I still have, in various projects, people start making optimizations without directly benchmarking. And then in the end, it turns out that their optimization and time put into it is useless because maybe the bottleneck was not in the place where they thought it would be. I've seen this a lot notably in people trying to optimize instruction, and in the end, like especially when people are using recursive algorithm, people think, okay, I can do least recent used optimizations, and in the end, it's not that what fastens the work, because for example, in terms of recursion, unrolling could help much more. So yeah, just to...
Yeah, so the question is about premature optimization,
yeah.
And I 100% agree with you. It's really easy to fall into the trap, even at the whiteboard stage, of talking through all the potential problems and coming up with solutions. And the earlier you can start benchmarking your code and see how it actually performs, the more you can avoid doing a lot of work that you don't have to. So totally agree. Any final questions?
I think are we out of questions? That was an excellent talk. Thank you very much, Alan.